All right. So what we have so far about the uh, natural log functions and exponential functions. Okay, so let me clarify and make a few details of those stuff. Uh, natural log and exponential functions. Okay, so we define first what is a natural log. So if we have a what do you call 1 over x, okay, starting from 1, and then x, we define a natural log as the integral of okay, 1 over x, sorry, because we use x here, so yes, dt over t. So that means this is the area of that area over there. Okay. This is for x positive only. Okay. So that's what we call the exponential log functions, natural log functions, and with properties uh, like a log functions. Okay. Like log functions with some base. Okay, so what is that? Ln of, if you compute Ln of a product, then you have sum. Or if you Ln of a quotient, then it is a difference. And if you take Ln of a power form, then the power just factors out. Okay, so this log functions. All right, and you have the calculus for this one. Okay, because by definitions this, and then you have the derivative. Sorry. Is just 1 over x integral of, sorry, and integral of there, calculus. But one important thing is that ln of x, these functions, is monotonically increasing. Therefore, 1-to-1 ejective. That means it has inverse. Which is called EXP. So if we draw the pictures, right? So this is the ln. So this is 1 over t. This ln of 1 is 0. Okay. And the this is diagonal. X. So the oh sorry, this is So this is the inverse. So this is exp. The red one is ln of x. Okay, so if you define from the beginning, ln, the domain for ln is from 0 infinity, 0 excluded. Okay, range is, yes, okay, so oh, sorry, because this is from there, the whole thing. Okay, so the inverse will exchange this domain in range. So domain of exp is just the range of ln. Okay, that means the whole thing. Okay, but the range of exp is just the domain of ln, which is the r, I say just r positive. Okay, so this is what we have so far. Okay, so exp is computable for any real number. Okay, all right, and we'll see that we define E as the E is the number um, so that ln of x, sorry, ln of E equals 1. All right. So remember that ln is the area of this. From 1 to E, so that the area equals 1. Okay, so you should slide E to the left or to the right, so you get it 1. Okay. So if you uh, compute ln of say 2, for example, you get, I'll pick your calculator. See, calculator. So, up to ln of 3 is, so this is more than 1. Okay. So the number E from here, E is between 2 and 3. Okay. So if you try down ln 2.5, for example, ln 2.5, 916. So from here, you get E is between, so 2.5 and 3. Okay, let's see ln of 2.75 then. ln 2.75. This is already exceeding 1. Okay, that means E must be between 2.5 and 2.75. Okay, keep dividing by 2. So let's see, which should be the 2, 5, 6, 6 to 5. Okay, so 10. Of 2.625. Okay, so below 1. So below 1, that means E must be between and there. And you can keep going on. Get that E. That's the what we call the Euler. So that's why there's E, Euler constant. Okay. All right, so now uh, this exponent is defined. Uh, defined for a rational number. Okay, so what does it mean? Well, exponents is a, okay, let's see that. So for example, 2 power 3, that is 2, 2, 2, that's 3 times, right? 2 to the power of negative 3. You know this should be, right? Okay, so 2 to the power of, we can say 1/3 now. So 1/3 is there. This root, third root. Okay, and what is 2/3? Well, 2/3 means that 1/3, and then you square it. Okay. So in general, two P over Q is that, well, this you can, well, the Qth root of 2, and then raised to the power of 2. Or you can think also this way, to the power of P, and then take the square root. Okay, so that's what I mean by exponent is defined for any rational number. Uh, the thing is, here's the comes the problem. What if we compute something that looks like this one? uh, say 3 to the square root of 2. What does it mean? Token 2 to the power of pi. Okay. So we don't know how to compute this thing. Okay. So we will try to compute this one, right? So how we do this implementation? So this is the purpose of what we discuss using EN. Sorry, using ln, natural log n, the at exp. Okay, so that's the reason e to the x, so this exponent, I should say this exponentiations of the number e, that is defined only for, let's say, for x rational number. Okay, so this is uh, the problem with the e to the x. Okay, but remember, however, the xpx is defined for all x, including irrational. Okay, so here's what we and let's see, um, and further we know that the xp of, let's see, we get, okay, so we define this e to the x at the exp of x. Okay, so this is how we define it. So now e to the x is defined, the e to the x is now defined for any real number x. Okay, so this is the story of the function exponential of x. So this is actually e to the x. Okay, so then we have the properties. For example, e to the 0 is 1. Okay, so because this is the inverse, e to the a plus b is um, exp a plus b, right? But exp has the properties of the sum becomes product. E to the a, e to the b. Likewise, if you subtract and you get something that looks like this, a over e to the b. Okay, And inverse properties is that uh, e to the ln of x is just x for x positive. And let's see, what else? Oh, the other way around. Ln of e to the x is just x. That's for x real number. Okay. So because the e cancel the ln. All right, questions? And the nice thing about e is that that is the only function that has, if you take derivative, it won't change. And if you take derivative, it won't change this. Likewise, the integral is remains the same. Okay. All right, so now we can define exponentials of any numbers now. It's not only restricted to rational exponent of rational number. All right, so let's see what we pick up last time. Or derivative of any. Okay, so let's do the um, with the integral. We haven't done this integral. This derivatives, okay. So let's go to the textbook. Yeah, oh, okay, so get to that point later. Okay, so let's pick up something like this. Let's do this one, for example, or this one. Okay. So integral of x e to the x squared minus 3. Okay, so this is substitutions. Okay, use substitutions. In this case, u equals say x squared minus 3. Why? Because the derivative is just x 2x, and we have this x is just the multiple of the derivative. All right, so du is 2x dx. Right, so this. Right, so you do substitutions, you get 1/2 square root e to the u du. Okay, so this gives you integral of this. Again, this is u, c. So then you substitute back there. Okay. So another example is this one. Let's do 4t. E to the x divides by e to the x minus 1. Okay. Okay. Again, you use substitutions. Let's see, what's the substitutions here? So just say take e to the x minus 1. Okay. So du here is just e to the x. There, exactly. Okay, so you get du over u, which is ln of u plus c. Okay, and then you get u is this. Okay. Any questions? Right. If not, then let's continue with um, the general exponential and log functions. Okay. So this is the how we define um, exponential function for any base and any real numbers. Okay, so let's do this one. So we a be any positive number and x a real number. We define a to the x to be uh, e to the ln of a, sorry, x ln of a. Okay, so how come we have this kind? Well, compute the idea is from here. So e to the x ln of a is just e to the, let's see, x ln of a, right? We then we put x inside the ln. So this gives you there. Right? So a to the x. So that's the idea. And because e and ln cancel out, so you get a to the x. But then in order to have that, we got to have a to the x, but we have a to the x yet. Okay? So this is how we define it. Okay. So this is how we do this one. Okay, so this way we can find something that looks like now it is clearer how to, now we can compute, for example, what is 2 to the pi, for example. Okay, so 2 to the pi by definition is e to the, what is this, pi ln of 2. Okay, so we compute this you can plug in your calculator. Let's see, let's try it. E to the pi, where is pi? Pi times ln of 2. So then this gives you this one. Yeah. Okay, because you can plug in this to your calculator. Okay. Example. And what can we get from here? Let's see. Properties of exponent. I just copy this one. I won't write this thing, rewrite this thing. What is that thing? Step capture. Here. And, wait, that would. That's the properties of exponent. Okay. So the thing here is that how we compute the derivative and how we do calculus. Let's see how we do calculus. That thing. Okay. X of a to the x. Okay. So this is nothing but e to the phi ln of 2. Right? So the derivative of this is not pi, sorry. So x ln of 8. But ln of 8 is just a constant. Okay. So derivative is just derivative of let's see, chain rule. The chain rule times e to the x ln of 8. And this is but a to the x again. So we get a. And if you compare this, e to the x is just e to the x. So you have the extra term is this ln of 8. So then the integral of a to the x now is just the other way around. If you take derivative, then this gives you multiply by ln of a, and this is divided by ln of a. Okay, so nothing much special about this general exponentiations. Okay, questions? Okay. So let's do some more problems of this type. There we go. This is the thing that we write down. Let's do this one, for example. X cubed. Okay. Integral of 2x squared plus, yeah, just x squared. Easy because you substitute here u equal x cubed, then du becomes 3x squared dx. But you have this, right? So this is just 1/3 of integral 2 to the u there, du. Okay, so this is just 1 over ln of 2. Okay, so okay, and 2 to the u plus c. So you get 2 to the x squared x cubed over ln of 2 plus, sorry, plus c. Okay. All right, so to complete the cycle, let's know the general log functions. So again, here is just a x with a positive. So the graph looks like this one. There. It's just a to the 0 is always 1. Okay. So this is with a positive though. Sorry, a bigger than 1. Because for a less than 1, you get something that looks like this one. A less than 1. Why is it so? Because, well, just think about this one here. Think about, say, here, x equal 1/2. Yeah. Okay, because we know this can define as 1 over x. Okay, so now we know that 2 to the x, so it looks like this one. This is monotonically increasing. So 1 over this something increasing, then this should be something gets smaller and smaller. So this is so this is the difference. Okay, you see the domain is this is monotonically increasing. therefore injective, and it has inverse. Okay, so what is the inverse? Well, the inverse is, let's see, uh, the log base A functions. Okay, so then this is how we do this one. It's what we call, so logarithm base A. So A here is not A must be positive, and A cannot be 1 though, because if A is 1, 1 with any power is just 1. Okay, this is inverse. So what does mean, this inverse? That means if you compute y equals a to the x, then x is, sorry, this is y. Because if you apply this log base a to the y, okay, and you get log base a power a to the or x, this log a and this will cancel. So you get just x. Okay. All right, so how will you compute for example, this one? Well, you can use calculator, but the calculator only have log base 10 and has only a calculator only ln or log base 10. Okay, so how we compute this one? Okay, so you have change of a basis formula. Base formula. So how we do this one? All right, for example, if say y equals, so that means you can express x as a power of y. Okay, and if you apply ln to both sides, you get ln of x equals ln a of y. Okay, so but now y is an exponent, factors out, right? So now you can write y equals, y is log L, right? That is ln of x divides ln of a. So this is our change base formula. So now you can compute that one. Sorry, log is nothing but ln of 5 divided by ln of 8. Okay, so you can compute this one using a calculator. For example, ln 5 divided by ln of 3. Then you can compute this one. Okay. So logarithm with the base other than e is actually redundant. Okay. So that means, let's see, in more general, log a of x is just ln of x divides ln of a. And you write down something like this. Okay, so this is constant. Okay, so actually, log functions is a multiple, so ln of a okay. So using this uh, this idea, so take the derivative. If you compute the derivative, okay, remember this is just 1 over ln of a times ln of x. Take the out, the derivative of ln of x, which is just 1 over x. Only at this boundary. As a token, if you take derivative, sorry, out. Any questions? Okay, let's just do this one. I just computed here, so let's see how to do this one. Okay, using property of log. So we solve it for x. Okay, so there's it. Log 2 log minus log is actually log 2 over x plus 3 over x. Okay, so it is equals to, okay, and then take power of 2. So with cancel, so you get power. Okay, And then you can solve this. Let me see. Let's just do this. Look, x minus x plus 3 minus x. So for x, so base 2 of x plus 3 minus base 2 of x. Okay, so let's do this one first. If you write this down, just using one term, this becomes a quotient. Okay. Okay, and then power 2, exponent 2. So that means e2 to the okay. If you the exponent cancel the log, so you get okay. So you solve this one. But x is not for x on 0. All right, so you have, let's see, this is x equal -1, right? Sorry, what is this? So you can all right, so you get the solution. Okay, example. Yeah. So let's yeah. We compute the uh, and let's do substitutions. Do substitutions, then u equals square root. Okay, because du equals 1 over square root. Okay, dx. So then this gives you 5 1 over square root. This is the du. Okay, so you don't need this. Okay, and see what we get. Integral exponential, you get exponential back, but then you got to divide by this by ln of the base plus 3. Okay, so if we compute this one, that's 4. Okay. Oh, sorry, this should be okay. So you get root of x divided by ln of x with the base difference Okay, so this is not ln of x, but ln of 5. So you get ln of 5, but 4, 5 square minus 5, 1. Okay, 25 minus, so 20. Okay, any questions? All right, so let's take a break for 5 minutes, and we'll continue with the some more general exponentiations. Okay.